Welcome back, everybody. In this video, we'll be starting section 4.3, which is about the logarithm functions or logarithmic functions. And basically what it's about is about the inverses of the exponential functions. So if you need a review of inverse functions in general, take a look back at section 1.7 in our textbook. And basically the big idea is that the logarithm functions are going to undo the actions of the exponential functions. So there's a definition for us to read through here, and then we're going to see some examples. So we're defining this thing called a logarithm. It's going to have a base b, just like the exponential functions have a base. Every logarithm function will have a base. And the input to the logarithm is going to need to be a positive number, and it satisfies the following definition. For x's that are positive, which they'll always have to be, b needs to be positive, b needs to not be 1. Y equals log, that's the abbreviation for logarithm. There's a subscript of b, that's the base, and then we're taking a logarithm of x. That's equivalent to b raised to the y power equals x. Okay, so before I read off any more of that, I want to just go into a couple of examples. So for this, suppose that we have a base of 3, let's say b, a base of 3 for this. We know how exponential functions work. If we say for a particular base of 3, if I said, okay, well, what's 3 squared, you could tell me. 3 to the 4th power, you could tell me. If I give you an exponent, you can tell me the value. But what about going the other direction? If I asked you, okay, well, 3 raised to what power is 81? What exponent do you need to use to raise 3 to get 81? You think about it a little bit, you get 4, right? 3 to the 4th power is 81. You just figured out a logarithm. So you figured out that the logarithm with base 3 of 81 was equal to 4. Okay, let's try that again. 3 raised to some power is equal to 1/9. Well, I know that 3 squared is 9. How do you get it to be in the denominator? You make it a negative exponent, right? So that's -2. 3 raised to the -2 power is 1/9. So the base 3 logarithm of 1/9 equals -2. 3 raised to some power is 127. I know 3 cubed is 27. 3 times 3 times 3. Sticking it in the denominator, that means we need a -3 exponent. So the base 3 logarithm of 127 will equal -3. A logarithm essentially is an exponent that you need to use to raise the base to get whatever value you are given. Okay, so let's continue reading. Right there, we read log base b of x as the logarithm with base b of x, or log base b of x. A logarithm y is the exponent to which y must be raised to get x. Since the logarithm and exponential functions switch the x and y values, the domain and range of the exponential function are interchanged for the logarithm function. So the logarithm, its domain is going to be 0 to infinity. Okay, the inputs need to be higher than 0. The range for the logarithm will be all real numbers. Okay, let's try this some more. So here we have a base b of 5. And so we want to think, okay, well, log base 3 of 125. What power do you raise 5 to get 125? You cube it, right? So the base 5 logarithm of 125 is going to be 3, because 5 cubed equals 125. Okay, the base 5 logarithm of 125th, well, 5 squared is 25. We'd have to put a negative on it to stick it in the denominator, so that would need to be -2. 5 raised to the -2 power is 1/25. Okay, base 5 logarithm of 1 will be 0, because 5 raised to the 0 power is equal to 1. Any base raised to the 0 power is going to equal 1, And so this gives us the first of our log properties. The base A logarithm of 1 is equal to 0. The other one we'll have is that the base A logarithm of A is equal to 1 because A raised to the first power will equal A. So trying that with our 5. The base 5 logarithm of 5 is 1 because 5 raised to the first power is going to equal 5. Okay. All right, so here with a base of 4, okay, what power do you raise 4 to get 64? You raise it to the third power. 4 cubed is 64. So the base 4 logarithm of 64 is 3. Okay, for 256, that might be a little bit harder. Okay, 4 squared is 16. 4 cubed is 64. 4 to the fourth power is 256. So it's going to have to be negative 4 because it's in the denominator. That 256. Okay, log base 4 of 16 will be 2 because 4 squared is 16. The base 4 logarithm of 1 will be 0 because 4 to the 0 is equal to 1. Okay, in short, the base A logarithm of B is answering the question for you. What power do you raise A to get B? Okay, so we'll have some more examples next. Okay, so in the next set of examples, we want to see how we can rewrite expressions or equations in either exponential or logarithmic form. So in these first 5, we are given an equation in logarithm form. We want to re-express it in terms of an exponent. So thinking it through, let's try this with something really nice and familiar like 3 squared equaling 9. I know that 3 squared is equal to 9. And so 9 is, or 2 is the answer to the question, what power do you raise 3 to get 9? So the base 3 logarithm of 9 is 2. So you can kind of pattern match to do this. The base in each case is 3. What goes into the exponential function, that's the 2, is what comes out of the logarithm. What comes out of the exponential function, that's the 9, is what goes into the logarithm because they're inverses. Okay, so let's try. Here, the base 3 logarithm of A is equal to t. So 3 raised to the t power will equal A. Let's try that again. The base 2.1, whatever, logarithm of k will equal w. So here our base is 2.1. We'll raise that to the w power to get k. Base 2 this time. 2 raised to the 6.3 power equals m. Base 5 logarithm of 3 equals r. 5, that's the base still. The base is the same each time. We're putting r in, and 3 is coming out. Base 2 logarithm of t equals h. 2 to the h power equals t. So in those examples, we were changing from logarithm form to exponential form. So now a couple of examples where we go the other direction. So 2 raised to the 3.1 power equals x. So if we rewrite that as a logarithm, the base is 3.1. No, the base is 2. And then this is going to answer the question, what power do you raise 2 to get x? You're going to raise it to the 3.1 power. 6 to the p power equals m. So log base 6 of m equals p. X squared equals 19. Log base x of 19 equals 2. After you've done a couple of these, they get a little easier because it's the same but different. Log base 10 of p equals m. Okay, back and forth between log and exponential form. We'll see when we go on to solve some logarithmic equations why it could be useful to have an expression in one or the other. Okay. Out of all the different bases that you can use for logarithms, there's two that are most commonly used or most frequently used, one of which is 10, because we use 10, right? 10 fingers, 10 toes. Our system of counting is based on 10, so the base 10 logarithm is frequently used. And that's called the common logarithm, so we're going to define that right now. So a common logarithm is a logarithm with base 10. We write log base 10 of x, or if we leave the base off and just write log x, that's going to be assumed to mean base 10 log in this class. And so y equals log x means 10 raised to the y power equals x. And we'd read log x as the logarithm with base 10 of x, or log base 10 of x. Okay, so here let's just try it. The logarithm of 100. This is going to answer the question, what power do I raise 10 to get 100? So you're going to square 10, right? So log base 100, or log base 10 of 100 is going to be 2. Okay, the common logarithm of 0.001, which is 1,000, right? So we need to think, okay, well, that is the same as the logarithm of 1/1000 as a fraction. That might be easier for you. 10 cubed is 1,000. Getting that into the denominator means we need a negative exponent, so it will be -3. 10 to the -3 power is 0.001. Okay, of course, the common logarithm of 10 is going to equal 1 because 10 raised to the first power equals 10. Okay, that's the common logarithm. Like I'd said, well, more on that in a little bit. Okay, the common logarithm is frequently used if you have a calculator that you're going to use to do this, which you probably do. There's going to be two different types of logarithms on it. And one button, if you look and see an LOG button, then that's what this is about. Also, when you go to look, if you see a button for log, it's probably going to have a 10 to the x button that goes with it, like shifted or something. Okay, and so that's on the common logarithm. Okay, some graphs of logarithms. So we can lean on the work that we did for exponential functions to help us with the graphs of the logarithms. Okay, so we saw that for exponential functions, there were basically two different kinds of graphs. The functions were either increasing or decreasing, depending on whether the a was more or less than 1. In exponential functions, if the a is more than 1, it's going to be increasing, right? So that's what we'll consider here first. Shown to the right in blue is the exponential function. As you know, when you take an inverse, its graph will be the reflection across the line y equal to x. And so the logarithm graph shown here in red. Okay, for the logarithm, the domain is going to be 0 to infinity. The range will be -infinity to infinity because those are basically the range and domain swapped for the exponential function. The base a logarithm of 1 is 0 because a raised to the 0 power is 1. The base a logarithm of a will equal 1 because a raised to the first power is a. Okay, so there's two kind of important points on the graph of the logarithm. That's the point 1, 0 and the point a1. The graph of the logarithm for a bigger than 1 looks like that. That is going to be the most frequently seen graph because the two bases that we end up using for logarithms are both bigger than 1. Just for completeness' sake, though, we should mention if the a is less than 1, what is the graph going to look like? As you know, the graph of the exponential function is decreasing, and the graph of the logarithm is going to also be decreasing, and its graph will be the reflection of the graph of the exponential across that line y equal to x. It still will pass through the point 1, 0 and a1, but it will be decreasing. It has the same domain and range. That is, the domain will be 0 to infinity, and the range will be -infinity to infinity. As we saw with the exponential functions, depending on the base, you're going to get a different looking curvature for the logarithm functions. Mostly, like I said, with the exponential functions, you want to know these kind of qualitatively. You don't need to draw hand draw really beautiful graphs of the log base 3 of x, right? What you need to know is kind of the domain and range, the overall shape of the graph. Here it's for a is bigger than 1, they're increasing. They're going to all pass through the point 1, 0, and then they're going to pass through also the point A1 as well, which is harder to see on this picture. You'll notice also as they pass through the point 1, 0, the ordering of the graph switches. So you'll see counting from top to bottom, to the right of 0, you have red, black, blue, purple. And that order is reversed on the left side of 1 is purple, blue, black, red. Okay, so that's a quick tour through the graphs of the logarithm functions. Okay, we'd had the common logarithm. We also have a natural logarithm. We saw the natural exponential base, e, before, based on Euler's constant, about 2.718 and change, right? The natural logarithm is the logarithm that uses e as a base. We write log and then a subscript e of x for this, or the more commonly used abbreviation ln x. So the abbreviation for natural logarithm is lnx. You could argue, I guess, that it should be maybe NL for natural logarithm, but it's based on a Latin phrase, so that the word order is the other way around. And so natural logarithm is abbreviated LN. Okay, and the input needs to be positive, as before. And y equals ln x is equal to e raised to the y power equals x. Okay, and it's the exponent that e would need to be raised to in order to get whatever you're taking the logarithm of. Because e is this irrational transcendental number, it's a little bit harder to write down fun examples of this, but we can try. So the natural logarithm of e squared, this answers the kind of silly question, what power do you raise e to get e squared? You would raise e to the second power to get e squared. Okay. For natural log 5.8, this, we need to think backward on that one. So we need to have e raised to some power equaling 5.8. That is harder to do in your head, and so we're going to use our calculator to get the natural log of 5.8. So natural log 5.8 is about 1.757. Okay, so you can check and see if you've done that right, just about. So let me turn around and raise e to the power of 1.757. And I get about 5.795. Okay, which is pretty close to 5.8. Okay, the natural logarithm of 1 is going to equal 0 because e raised to the 0 power is equal to 1. The natural logarithm of e is going to equal 1 because e to the first power is equal to e. So there's a couple of properties of that natural logarithm. Because e is bigger than 1, it's going to have an increasing graph, as shown in the picture here to your right. It passes through the point 0, 1, and 1e. So right there is going to be e. Same domain, all real numbers, same range, the open interval 0 to infinity. Excuse me. All right, a couple of properties of logarithms. So we saw these kind of specifically for the natural logarithm and the common logarithm earlier, but I just wanted to go over these more fully. So for a positive base, here we're using a for the base. If a is positive and not 1, as our basis should be, the base a logarithm of 1 will always equal 0. The base a logarithm of a will be 1. And then those come from those corresponding exponent rules, that a raised to the 0 power is 1 and a raised to the first power is a. There are a couple of inverse rules. Those are numbers 3 and 4 here. And these are a little bit trickier to understand. It says the base A logarithm of a to the x equals x. And so what you can think of that as being like, as back when we were in section 1.7 and did inverses, when we said things like f inverse of f of x is just going to be x again. If two functions are inverses of each other and you form their composition, nothing happens. You should be back to where you've started. Number 3, we would do the exponent part first and then the logarithm. Number 4, you do the logarithm part first and then the exponential piece. Okay, so you get a couple of silly questions here. What power do you raise 3 to get 3 to the 7th power? You'd raise it to the 7th power, right? Okay, here, the base 2 logarithm of 32. This one we can actually think about a little bit more. The base 2 logarithm of 32, 2 raised to what power gives 32? 2 raised to the 5th power is 32. So if you raise 2 to that power, what do you get? 32, right? Like I said, those are a little bit trickier to kind of catch, but we'll have the occasion to use them from time to time. All right, I did want to mention something further before we do more examples. Going back to the natural logarithm. There we go. The abbreviation for natural log is ln in this class, and the common log is base 10. And that's true throughout this class, okay? If you are looking online or on Google or in some books published in Europe sometimes they use log to be base E log, okay? Also, some computer programming languages will use the symbol log for the natural log, and they'll have something called log 10 for the common logarithm, okay? So to make a long story short, for our class, ln is the base E log and log is the base 10 log. If you are doing computer programming, if you are doing logs and stuff on Excel, Microsoft Excel or other spreadsheets, then if you have a question about it, let me know, because it can be different. But for our class, ln for E and log for base 10. Okay, so I want to talk a little bit more about domains for logarithm functions. So we saw, so background first, we saw that exponential functions always were either increasing or decreasing, but they had as their range 0 to infinity, right? They were always quadrants 1 and 2 for their picture. So when you form the inverses, which is the logarithms, then you end up with the graphs being just in quadrants 1 and 4, depending again on whether the base is more or less than 1. But the deal is then that for exponential functions, you always get a positive number out. So for a logarithm function, you have to always put a positive number in, okay? So for a logarithm function, the input has to always be more than 0. So here, let's try. We want to find the domain in interval notation for each of these. So f of x is the base A logarithm of x. Domain, 0 to infinity. Okay, so that's that. That one was easy. The rest of them are not so easy. For the next one, number 2, f of x is the base 2 logarithm of x minus 7. So what goes into the log has to be positive. So what we need is x minus 7 to be greater than 0. So then x has to be greater than 7, actually. So then our domain in interval notation will be 7 to infinity. Okay, this is kind of like when we were dealing with square roots, you know, back in the day. We know that the square root had to have a positive input, and so its domain was 0 to infinity. And if you took the square root of x minus 7, the domain would have been 7 to infinity, right, in order to keep it defined as a real number. This is a similar sort of thing, okay? What goes into the logarithm has to be something positive. a difference between a log and the square root that I was just talking about is that we were able to take the square root of 0. You can't take the logarithm of 0. Okay? All right, so continuing on. The logarithm of 1 minus 2x. We don't need it to answer the question, but just to make sure you're paying attention, what is the base on this? It's base 10, right? If it's not written, you assume it's base 10. It turns out not to matter for this question because the domains on logs are all the same, but this would be base 10. Okay, so we'll have 1 minus 2x has to be positive. So 1 has to be bigger than 2x. 1/2 has to be bigger than x. So turning that around, x has to be less than 1/2. So negative infinity up to 1/2. And then if you're concerned, like I thought you said a minute ago that it had to be positive, and there you go saying it's negative. Well, here we're not taking the logarithm of just x. We have the logarithm of 1 minus 2x. So in order for the input to the logarithm to be positive, x has to be under 1/2, right? So try plugging in some values for x here and make sure that you understand how that's playing out. Okay, we have two more. For number 4, g of x is the natural log of 2 over x squared minus 4. So the input there has to be greater than 0. So I know fraction's positive. Well, 2 is positive. So the whole fraction is going to be positive if x squared minus 4 is positive. So we need x squared minus 4 to be positive. Okay, so there's several ways of doing this. You could do this using a sign chart. I think it's easiest to do this using the graph. This is not the graph of the logarithm. I need to know where x squared minus 4 is positive. That is a quadratic function with vertex at 0, -4, right? Okay, where that will be positive will be to the left of -2 and to the right of +2. Okay, so that would be the domain here. That would be enough to ensure that that output or that input is going to be positive. All right, so let's try one more of these. So I guess we got 2 more. So here we have the logarithm of x squared minus x minus 6. So we need to know x squared minus x minus 6 is greater than 0. So again, you could do this using the graph, which is probably easiest. I'm going to do this using a sign chart though, just so that you have an example of what that looks like. Either way, we're going to want to factor that left side. So we've got x minus 3 times x plus 2 is greater than 0. So I know from arithmetic that if you multiply a negative times a negative, you get a positive, or a positive times a positive, you get a positive, and otherwise you get a negative. So I'm going to make a sign chart to show what's possible. And then for the cutoffs, I'm going to use the 2 zeros of our polynomial. So this will be -2 and +3. Our factors are x minus 3 and x plus 2. I'm going to pick out test values inside of each interval. So a number bigger than 3 would be 10. A number between -2 and 3 would be 0. And a number smaller than -2 would be like -8. Okay, I'm just picking numbers that are interior to the interval. Then we're going to substitute our test numbers into each factor. I don't care what the value is, I just need to know if it's positive or negative. So starting with 10, 10 minus 3 is positive. 10 plus 2, positive. Take the middle column next. 0 minus 3 is negative. 0 plus 2 is positive. -8, -8 minus 3 is negative, and -8 minus 2 is negative. Okay, again, going back to your arithmetic days, you know that a negative times a negative will be positive, and a positive times a positive will be positive. So where is the domain in the end? It will be negative infinity to -2, and then from 3 to infinity. Okay, and that's it for that one. You can go back if you wish and try the sign chart way on number 4 and confirm that you get the same answer if you want the practice. Okay, for number 6, we could do this in the same way as we did. That is really similar to number 4. We could do this basically the same way as we did number 4. Or we could do a sign chart. I think the graph will go faster, so let's do that. Base 2 logarithm, that's okay, doesn't matter, of 5 over x squared minus 9. We need 5 over x squared minus 9 to be positive. Okay, well, I know 5 is always positive, so it boils down to whether or not x squared minus 9 is positive. Again, thinking about the graph, that would be a parabola that has as its vertex 0, -9. Its x-intercept would be at 3, 0, and -3, 0. So where is this thing positive? -infinity to -3. And from 3 to infinity. Okay, I'm going to put the sign chart way in here, just kind of for, so you get an extra example of it. You can do either the sign chart or the graph, either way. All right, so this is how the sign chart way works out. I chose test values of -51, 0, and 10. The x squared minus 9 factored as x plus 3, x minus 3. So I drew a number line and put the zeros of those two factors on the number line, -3 and 3. I wrote the two factors, x plus 3 and x minus 3. I chose the test values of -51, 0, and 10. I tested each of those test values into the two factors, x plus 3 and x minus 3, and just recorded whether or not I got a positive or negative answer. Again, we know that a positive times a positive or a negative times a negative will be positive. So we're going to select those intervals from -infinity to -3, and then from 3 to positive infinity. All right, so that does it as far as domains goes. And that'll finish this video. We're not quite done with this section. I just wanted to do some more examples, and those will wait to the next video. Let me know if you have any questions in the meantime, and have a great day.